Section: Overview. In this section, we explore how the early days of computing introduced time sharing, significantly enhancing user productivity and hardware utilization but also presenting new security challenges. This was mainly because computers began to be shared among multiple users, necessitating measures to prevent unauthorized access and protect private data through isolation. Similarly, the field of machine learning, ML, is currently undergoing a comparable phase. The need to reduce hardware costs and achieve high utilization rates is leading to the sharing of ML model accelerators among various users. This situation raises an important question: does this sharing introduce new security concerns? We demonstrate in our work that using a mixture of experts, MO, approach, particularly within a transformer architecture, can expose a vulnerability. Specifically, an adversary can manipulate the model's predictions for data belonging to other users who are grouped into the same batch. This issue arises because many routing strategies, which are responsible for assigning inputs to experts, do not maintain consistency across different batches of data. This vulnerability is present in current MO implementations that limit the number of inputs an expert can handle by setting a buffer capacity. We describe two methods for generating adversarial data, both of which enable an attacker to compromise the integrity of the model by causing deterministic faults, and its availability by denying access to certain experts for legitimate users. We then explore several strategies to mitigate these attacks, either by completely preventing them or significantly reducing their effectiveness. Delving into the technical details, we first explain the concept of MO and its sparse variants. In a deep learning context, an MO layer processes an input token by combining the outputs of multiple experts, each weighted by a gating function. This gating function determines the importance of each expert's output for the given input. In a sparse MO setup, the gating function assigns significant weights to only a subset of experts, reducing the computational cost since not all experts need to be evaluated for every input. Typically, the top K experts, as determined by the gating function, are selected for evaluation. This approach not only saves on inference costs but also aims to enhance model performance by effectively utilizing a smaller number of parameters for each input. We also examine the routing strategies used in transformer models employing MO, where the input consists of sequences of tokens. Each token is assigned to experts based on weights calculated by the gating function. However, the method of assigning tokens to experts can lead to imbalances, where some experts are underutilized. To address this, a buffer capacity limit is often set for each expert, determined by a capacity slack variable. This limit controls how many tokens each expert can process, aiming to balance the load among experts. In summary, our investigation highlights the security implications of sharing ML model accelerators and demonstrates how the MO approach, despite its advantages, can introduce vulnerabilities when not carefully managed. We propose solutions to mitigate these risks, ensuring the integrity and availability of the models are maintained. Section Summary. In this section, we demonstrate that the use of mixture of experts, MO, in models like transformers can lead to security vulnerabilities, allowing adversaries to manipulate predictions for other users in shared environments. The vulnerability arises from routing strategies that are not order invariant across batches, affecting current MO implementations with input capacity limits per expert. We propose two adversarial data generation methods that enable integrity and availability attacks, and explore mitigation strategies to counter these threats effectively. Section: Threat Model and Attack Method. In this section, we discuss our threat model and the method we use to carry out attacks. Our approach takes advantage of the way mixture of experts, MO, routing works, specifically focusing on the finite-sized buffer queues assigned to each expert. When these queues become full, tokens can either be dropped or redirected to another expert with available space in their queue. This characteristic opens up a new avenue for attacks. By mixing adversarial data with regular user data in a batch, the adversarial data can manipulate the routing of benign data by overloading certain experts' buffers. We illustrate the entire attack process in a figure within the paper. Under the standard routing strategy, tokens are assigned to experts in the sequence they appear in the batch. This sequential assignment means that inputs at the start of the batch can influence where tokens later in the batch are sent. For example, consider a batch with 2 data points, each containing 2 tokens, and 2 experts each with a buffer capacity of 2. If all tokens are meant to be sent to the first expert, the buffer for this expert will fill up with the tokens from the first data point, leaving no room for the tokens from the second data point. This scenario highlights a key point. The assignment of tokens to experts depends on the batch composition, allowing one data point to alter the expert assignment of another. We exploit this dependency between batch routing to identify adversarial data points that can negatively impact the output of other data points in the batch. Our setup involves a transformer model that uses Mo layers, parameterized by a set of weights. This model takes a sequence of tokens as input and outputs a probability distribution over a vocabulary. We assume that in a given batch of inputs, the adversary controls all but one of the inputs. The adversary can also control the order of batch elements, ensuring that the target input is last. The goal of the attack is to find adversarial inputs that change the predicted next token in the sequence after the target input from its expected value. We achieve this by optimizing the adversarial inputs to minimize a specific loss function, which compares the output at the target token with the maximum output for any other token. We use a simple random search to construct these optimized adversarial inputs, randomly sampling subsets of tokens from the vocabulary and checking if they decrease the loss for the target input. This attack assumes the adversary is working with a black box model that uses Mo and can observe the model's output logits. It also assumes the adversary can ensure their data is batched with the target data point. We do not make any assumptions about the Mo configuration, other than it has finite per expert queues and uses a batch order dependent routing strategy. This assumption is not far-fetched and reflects the operation of many Mo-based transformer models in practice. Section Summary. In this section, we introduce an attack method that leverages Mo routing with finite buffer queues for each expert, allowing adversarial data to influence benign data routing by filling expert buffers. By exploiting inter-batch routing dependencies, our attack aims to negatively impact the outputs of other data points in the batch. The attack setup involves optimizing adversarial inputs to change the model's predicted token sequence, achieved through a random search process detailed in the algorithm provided. Section: Attack Demonstration. In this section, we showcase our attack on a widely used open-source Mo transformer model named Mixtral 8x7b. This model has a vocabulary of 32,000 words, operates with 8 experts for each layer, and allows each word to be assigned to up to 2 experts. We chose the prompt, blue solve the following equation. 1 + 1 =, which consists of 12 words as our target. We found that the model's most likely next word prediction was green 2 inches, with a probability of 25.9%. We worked with a batch size of 8, resulting in a total of 96 words in the batch. The default setting of Mixtral 8x7b does not limit the number of words an expert can handle, making it immune to our attack in its original form. To proceed, we modified the model to use a basic routing strategy with a limit of 38 words per expert, out of a potential 96, without affecting the model's prediction for our target prompt. However, this limitation is expected to impact the model's performance on longer sequences. We set the number of attack iterations to 1000, altering 5 words in each of the 7 data points within the adversarial batch per iteration, totaling 35 words out of a possible 84. The results, illustrated in a figure, initially showed green 2 inches as the most probable next word. However, as the attack progressed, red 1 became more likely due to the reassignment of words to experts, particularly after 60 iterations when the buffer of the second expert was filled with words from the adversarial batch, excluding the word from our target prompt assigned to this expert. We also explored the possibility of transferring the attack to different prompts, aiming to demonstrate that errors could be induced in model outputs on prompts not specifically targeted but included in a batch with the adversarial data. This would suggest the feasibility of untargeted attacks, where the adversary blocks experts preferred for specific tasks like arithmetic or translation. Our tests on arithmetic prompts similar to our target showed that the attack could indeed transfer, affecting the model's predictions on these prompts. This provides anecdotal evidence that adversarial data can induce errors in model outputs on unseen prompts. Lastly, we investigated whether the position of a data point within a batch affects its vulnerability to our attack. We found that any expert routing strategy with a buffer capacity smaller than the total number of words in a batch is susceptible to attacks aimed at overloading certain experts. Data points positioned later in the batch are more at risk under a basic routing strategy that assigns experts sequentially, as earlier points can alter the expert assignments of later ones. However, by always placing our target prompt first in the batch, we observed that the attack did not induce an error in the model's output on our target. This suggests that while the position can influence vulnerability, the assignment of words to multiple experts can still affect even those data points placed early in the batch. For instance, if both our target and the adversarial data aim for the same expert but the buffer fills up, the later data point's words could be reassigned, demonstrating the nuanced dynamics of expert assignment under attack conditions. Section Summary. In this section, we demonstrate an attack on the MIXTRAL 8x7B model by setting a target prompt and modifying tokens in an adversarial batch to influence the model's output. We show that altering expert assignments in the model can lead to changes in predicted tokens, even transferring errors to different prompts, and highlight the vulnerability of expert routing strategies based on batch position. Section. Attack sensitivity to buffer capacity to limit. In this section, we explore how the sensitivity of an attack changes with the capacity limit of an expert's buffer. We find that the smaller the limit on how many tokens an expert can handle, the easier it becomes to disrupt the process by finding adversarial tokens that prevent the target input from being assigned to its preferred expert. We conducted experiments with various buffer capacity limits and observed that attacks are more successful when the buffer size is smaller. As the buffer size increases, it becomes more challenging to interfere with the expert assignments of the target input, leading to the failure of the attack. We also introduce an example of a denial of expert attack. Previously, our goal was to cause the model to make errors in its output for a specific target input. Achieving this by overflowing an expert's buffer or altering the routing assignment was just a means to that end. However, we now demonstrate that we can directly aim to fill up a specific expert's buffer. By setting the buffer capacity limit to 20 tokens per expert, we adjust our approach to specifically target the buffer of the third expert in the first layer of the model. This requires us to have in-depth access to the model, as we need to monitor the expert's buffer closely. Our results show that initially, 6 out of 12 tokens from the target input were processed by this expert. Within 28 iterations, we managed to find a set of adversarial tokens that caused all these 6 tokens to be dropped. To counter such attacks, we discuss potential mitigations. The attack leverages two optimizations in the model: the use of expert buffer capacity limits and batch-dependent expert routing assignments. If we remove the buffer capacity limit or set it to the total number of tokens in a batch, the attack becomes ineffective. This was confirmed in our tests with a default routing strategy that does not impose a buffer capacity limit. However, setting buffer capacity limits is beneficial for optimizing hardware use, as it prevents unnecessary computation and memory usage. We suggest several other mitigation strategies that, while not foolproof, can reduce the effectiveness of the attack. These include randomizing the order of inputs in a batch, using a larger capacity slack, and sampling from gate weights for expert assignment instead of selecting the top K experts directly. Each of these strategies was found to hinder our attack when implemented. In our discussion, we highlight that combining queries from various sources can improve hardware efficiency but also opens up vulnerabilities. The machine learning community is aware that performance can be impacted by dropping tokens or misrouting them. We urge the community to also consider the security risks associated with outputs that depend on the combination of inputs from different batches. While the practical implications of our attack on deployed models are still uncertain, we see clear directions for future research. This includes developing more efficient attacks, understanding the impact of variance in model outputs due to token dropping or random expert assignment, exploring different routing strategies, and investigating how training models with load balancing can increase resilience to attacks. Lastly, we have not yet looked into models fine-tuned with specific instructions, which are likely to be used in security-sensitive applications, and this remains an area for future exploration.